So next up we've got compound interest, which is where things really start to get kind of interesting. So instead of just a simple interest payment where we take our interest at the end of the payment period and we spend it or hoard it away somewhere, the idea here is that at the end of each payment period, so we receive that interest, instead of keeping it, we reinvest the interest. We reinvest the interest for the next payment period. So the next time we earn interest on the next payment period, we're not going to earn interest on just the original principal, we're going to earn interest on the original principal and the interest that we just reinvested. Right, so this is the concept of compound interest. You're earning interest, you're reinvesting it, and then the next time you earn interest, you're going to earn even more. It's compounding on each other. So I want to do an example of this, but I need a whole board, so let me just reerase all of this really quickly. So suppose you deposit, we'll keep the numbers nice and simple here. Suppose you deposit $1,000 in a bank account. In a bank account that pays 8%. So the annual rate is 8% and it's compounded quarterly. This is quite a nice account. Compounded quarterly. I'm missing an R there. Compounded quarterly. So let's just suppose we do this, right? We put in $1,000. The interest rate is 8% annually, but it compounds quarterly. So every quarter, at the end of each quarter, we're earning interest on our investment. So after one quarter, what's the amount in the account? Well, it's going to be, we use our formula, A is P times 1 plus RT. Right, so principal, we invested 1,000. 1,000 times 1 plus R, 8%. Times T. How many years has it been? Well, it's compounded quarterly, so after one quarter, there's 4 quarters in a year, so 1 quarter over 4 quarters. Alright, so you plug this into a calculator. This is 1,000 times 1 plus 0.02, so 1,000 times 1.02, this is just $1,020. Alright, so there's the amount after 1 quarter, right? 8% interest rate. 1 quarter is 1/4 of a year, so there's after 1 quarter. How about after 2 quarters? Well, here's the difference. Right, the difference is that the principal is no longer 1,000. After at the end of the first compounding period, 1 quarter, we reinvested this $20 interest that we made. So our principal now, starting off, is 1,020. And then times 1 plus RT, this hasn't changed, this is still 1 plus 0.08 times 1 quarter. Plug this into a calculator, you get that this is $1,040 and 40 cents. So you notice the interest earned after the first quarter was 20 bucks. But after the second quarter, in the second quarter, we earned, what's the difference here? $20.40. So a little bit more interest because our principal is a little bit bigger. And now we take this principal and we reinvest it. So after 3 quarters, the amount, our principal is now 1,040.4 times 1 plus RT, this never changes, 0.08 times 1 quarter. This is now 1,061 and 21 cents. And we'll just go a full year here. So after 4 quarters, now we take this, we reinvest. So this is $1,061, and we've got our principal is 1,061.21 times the same interest rate, 1 plus 0.08 times 1/4, to get that this is 1,082 and 43 cents. So notice, by the way, if I just collected this yearly, I would have started off with $1,000, 8% paid annually. At the end of a year, I would have made $80, right? $1,080 would have been my output. So this whole compounding, quarterly, reinvesting our interest has made us a little bit of extra money. And I want you to think about what's actually happening here, because we don't want to sort of have to compute compound interest this long way every single time. Every single quarter, 1 quarter, 2 quarters, 3 quarters, 4 quarters. We want a nice formula that outputs the final amount at the end of the day. So what's really happening? Well, we're just taking this amount, right? Our original principal, 1,000. 1,000, we multiply by this number, 1 plus 0.08 times 1/4, right? We get out an output. Then we take that number and multiply it by 1 plus 0.08 times 1/4. We get out an output. We take that number, multiply it by 1 plus 0.08 times 1/4. Take that number, multiply it by 1 plus 0.08 times 1/4. So all we're doing is multiplying by this thing, this expression, 1 plus 0.08 times 1/4. We're just multiplying by that over and over and over again. So there's an exponential thing happening here, right? It's our original principal times this guy raised to some number. In this case, it's raised to the power of 1 for 1 quarter. Here we multiplied by it twice. To get 1,020, we multiplied by it once, and then again to get 2 quarters. So it's really this guy raised to the power 2, then to the power 3, then to the power 4. So let's write down a nice formula for compound interest. So here's our formula. Our formula for compound interest is has a whole bunch of the variables you're used to seeing except for one, m, but the compound interest formula is a, so the future amount, a is the future value, is equal to p, the principal, the present value, times 1 plus r over m. Here r is the standard annual rate you're used to working with in decimal, but m is the number of compounding periods per year, how often this account is paying out interest. So m is the number of compounding periods per year, and then, like I promised, this would be an exponential formula to the power of mt. So m is the number of compounding periods per year times t, the time in years. And there's the formula. I feel like this is the more standard formula. If you look up compound interest formula, you'll see this sort of written in most places. But the textbook seems a little bit more partial to a slightly different form. And you'll see this form in some of the homework problems as well. So, or a is just p times 1 plus I to the n. So all they've done here is they've substituted in a couple of things. Actually, let's go slightly different order. N is just m times t. Right, so it's it's the total number of compounds. So this is the total times compounded. And I is of course r over m. So that's taking our annual rate and sort of normalizing it. It's the rate per compounding period, if you want to think of it like that. Again, let me not put an equal, so we'll just put in brackets here. This is the rate per compounding period. Okay, so you'll often see this formula given in the textbook, but they're exactly the same thing. Just they've called this r over m. They've given it a name. They called it I. It's the annual rate divided by the number of compounds, so it's rate per compounding period. And then MT, this is sort of the total number of times that you get compounded, so they replace it with N. It's MT, it's the total times, the total number of compounds. So this immediately leads into an interesting example of what happens if you compound more frequently. So as opposed to compounding per year, what if you compound per quarter, per month, per day? So let's look at this. Okay, so we're going to look at a whole bunch of different compounding periods here, but we're going with nice numbers. Find the amount after 5 years if $1,000 is invested at an annual rate of 5%, or sorry, 8%, and first up, compounded annually. So we'll use our compound interest formula. A is P times 1 plus R over M to the MT, and we just have to plug in some values, right? So the future amount, the A, is going to be principal, 1,000, times 1 plus R, the interest rate, 0.08, over M. So this is the number of compounds we have per year. Well, if we're compounding annually, the number of compounds per year is just 1, right? So this is just over 1, times MT, so M we agreed was 1, and T, we're asked to do this after 5 years, so 1 times 5. You'll plug this into a calculator, and you'll find that this is equal to, well, how about I do one more line. This is 1,000 times, what is this? This is 1.08 to the 5, and this is 1,469.33. So not a bad return, right? After 5 years, you've almost got half again what you originally invested. But how about if we compound, let's say quarterly? Okay, so A, once again, this is P times 1 plus R over M to the MT. Still plugging these values again, principal doesn't change, this is still 1,000. Times 1 plus the rate doesn't change, 0.08. The only thing that's really going to change here is our compounding period, it's M. So how many times do we compound per year now? If we compound quarterly, well, there's 4 quarters in a year, so this is divided by 4. M is 4. To the power of MT, so we've got 4 times 5 years. Alright, so once again, that's 1,000 times 1.0, what is this? 0.08 divided by 4 is 0.02, so 1.02 to the power of 20. Alright, so plug that into a calculator, and I get 1,485.95. What do you notice? Well, you should notice that this value is a little bit bigger than this one. Same time period, same original, same time period of 5 years, same original principal, same original investment of 1,000, same annual rate of 8%. And yet if I compound quarterly as opposed to annually, I earn a little bit more money. So compounding quarterly is better than compounding annually. What if we push this a little bit further? What if we do it, let's say monthly? Monthly. So once again, A is P times 1 plus R over M to the MT. Same principle, 1,000. 1 plus 0.08 over, same rate. But how many compounding periods now? Well, there's 12 months in a year, so we compound 12 times. And then to the power of 12 times 5. So this is what? This is 1,000 times 0.08 over 12 is 8 over 12 is 0.667, so this is going to be 1.006. Yeah, this continues forever, 6666. What is rounded? We'll say 0.067. And this is, maybe I should go one more decimal place, right? Let's be careful with our rounding. 67, so the power of 12 times 5 is 60. And you plug this into a calculator, you compute it, and you get that this is 1489.85. So again, what's the observation? This is a little bit bigger than this, about $4 bigger, $3.90 to be precise. But if I compound monthly, again, same interest or same interest rate, same principal invested, same time period. But if I compound monthly, I make even a little bit more money than I did if I compound quarterly, which again was even more than compounding annually. So the question is, it's clear, I hope, that the more frequently you compound, the more interest you make at the end of the day, the bigger the account total. But the question is, what happens if I compound even more frequently? Instead of monthly, what if I compound daily, or hourly, or minutely, or even every second? What happens if I compound continuously? Well, this number isn't going to grow to infinity. It's asymptotically approaching some sort of asymptote. And I'll tell you what the answer is. So this is the question I was posing, right? Again, we've observed that the more compounding periods, the larger the future value. So what happens if you compound every hour, every minute, every second? What happens if you could compound continuously? So you're just constantly earning interest, it's constantly compounding all the time. Well, the answer is that it doesn't blow up to infinity. A doesn't blow up to infinity, but it approaches some sort of horizontal asymptote. So interest earned or compounded approaches a horizontal asymptote. So what I'll do now is just give you the formula. There is a special formula for the continuous case, and it's the continuous compound interest formula. Sort of interesting because it's the ideal case. So if a principal P is invested at an annual rate R, compounded, and there is no number of compounds here, it's just compounded continuously. So there's the catch. This is when this particular formula applies, is when someone tells you we're talking about continuous compounding. Then the amount A after T years is given by the following formula. A is P, so future amount A is equal to P, the principal, as always, times e to the power of RT. So R is the annual rate, T is the time period in years, E is this number we've talked about with logarithms, is 2.72 something or other, but it's just a fixed constant. And I want to warn you that when you're using this formula, don't round this. Don't round E to 2.72 or whatever. When you're plugging things into your calculator, there will be a button for E that will give you a precise value for E. Use that. Don't round, because when you're talking about this value, A to cents or whatever, if you round this, you can be off by quite a significant number. So don't round until you get to the very end. But there's the compound interest formula. It's sort of the limiting case. So if you compound every hour, every minute, every second, what if you could just do it continuously? Well, here's the formula that you get out. If you want to read the derivation, it's somewhere in the textbook. You can see sort of, I'm not sure how rigorous the argument is, but at least a heuristic argument as to why this formula works. But if not, there's just there's the compound interest formula. And we'll do an example. Alright, so here's our example. What amount will an account have after 1.5 years, 1.5 years, if $8,000 is invested at an annual rate of 9%? And there's two cases here. First is 9% compounded weekly, and second is 9% compounded continuously. So in truth, there's actually not a whole lot to these problems. We just have to use our formulas. So for the discrete compounding case, the number of compounds, our formula is A is P times 1 plus R over M to the MT. And we just have to plug in our values. So what do we have? Our principal is $8,000. 8,000 times 1 plus our rate, 9% is 0.09, over the number of compounds, M. So we're compounding weekly, there's 52 weeks in a year, so 52 compounds, to the power of MT, so 52 times 1.5 years, MT. And at this point, you go ahead and plug this into a calculator. Again, be careful not to round until the very end, but if you do that, you will get 9,155, and here's where the rounding errors will come in. If you do round, you might be off by a cent or so, 0.26. Again, unless MyMathLab specifies otherwise, round to the closest cent. And if we want to do the same thing but compound it continuously, well, now we use a slightly different formula. We use our continuous compounding formula. A is P times e to the RT. But once again, we just plug in our values. So P is 8,000. E is that fixed constant that we'll use our calculator to plug in. And R is the same thing, 0.09. And T, number of years hasn't changed, still 1.5. Plug this into your calculator. Again, use the little E button on your calculator so it doesn't round it, it gives you an exact answer. And then finally at the end you'll round to the closest cent. And this comes out to, remember I should be expecting this to be just a little bit higher than the compounded weekly number because it's continuous, so it should be a little bit better, but not much better. And this is 9,156.29. So again, it looks like a reasonable answer. It's not like 11,000 or something or a million. It's just a tiny bit bigger than if we compound weekly. So the formulas aren't hard to use. You just have to know the formulas and be able to plug in the numbers. But we are going to use them in a slightly more advanced way. Instead of asking what the future amount is, how about we ask how long it takes something to happen, or how much do we have to originally invest to have a future value? And we'll do those now. I think those are much more interesting problems. So here's the question. How much should new parents invest at 8% to have $80,000? $80,000 towards their child's college education in 17 years if interest is compounded semi-annually. So we're looking at a semi-annual compounding case, not the continuous case. So we know we're using this formula. We're using A is P times 1 plus R over M to the MT. And essentially we're told we know our future value is going to be 80,000. We're asked to find this. We're asked to find what's the amount we have to invest. What does P have to be so that A is equal to 80,000? Given that we know R is 8%, number of compounds per year, compounded semi-annually, so twice, and the time period is going to be 17 years. So we'll go ahead and we'll plug all these things in. Sometimes I solve for P first, but in these complicated cases it's easier just to have some nice numbers to work with. So we'll just plug in all the values right now. 80,000 is equal to P times 1 plus R, 8%, 0.08. Compounded semi-annually, so RM is 2, times, or to the power of 2, times 17. So that's 80,000 is P times 0.08 divided by 2 is 0.04, 1.04 to the power of 34. And we're solving for P. We want to know what's the original amount we have to invest, so now you just solve for P, divide both sides by this expression. P is 80,000 over 1.04 to the 34. And at this point you plug in everything into your calculator. Notice I haven't done it yet because I don't want any rounding errors. But you'll plug it all in now, and then you'll round to the closest cent. And this comes out to $21,084.17. So we can do a lot more with this formula than just solve for the future value all the time. We can ask what's the initial principal we have to invest to have a future value in a given time frame, which is again a real world sort of interesting type of problem that people run into all the time. How much money do I have to invest now to have a future amount? Another really interesting type of problem is how long is it going to take me to reach this future amount that I need? So let's do one of those. And mathematically, they're much more interesting to solve for t because it's in the exponent, which means we need to invoke logarithms. One more thing I'll say is I could oppose this exact same problem, but asked if it's compounded continuously, and then you would have to use a different formula, right? You'd have to use a equals p times e to the rt, but it's just a different formula. The math is still the same. So here's the type of problem I was talking about. How long will it take $10,000 to grow to $12,000 if it's invested at a rate of 9% annually, but it's compounding continuously? Okay, so we're in a continuous compounding case, so we'll use our continuous compounding formula. A is equal to P times e to the RT. And we're given the future value. We know our future value, we want this to be 12,000. Our principal we invest is 10,000. E is just our fixed constant. We know our rate is 0.09. And we're asked to solve for t, right? How long will it take? So t is the unknown. T is the unknown quantity we want to solve for. But plugging in everything, we have this equation. Now we want to solve this equation. Well, here's the problem. The thing I want to solve for, t, is stuck in the exponent. How do we get things out of the exponent? We use logarithms. But before I deal with logarithms, before I take logs of both sides, I want sort of just a base to a exponent. I want to get rid of this constant in front. So let's divide both sides by 10,000 first. 12,000 divided by 10,000 is just 1.2. Okay, canceling all the zeros and everything, it's just 1.2. Equals e to the 0.09t. So now how do you get stuff out of the exponent? You take logs of both sides. Namely, we use natural logs. So I'm going to take the natural log of both sides. Ln of 1.2 is equal to ln of e to the 0.09t. Why did I do that? Well, because of our log property that says when you have an exponent inside of your log, you can bring it outside as a constant multiple. So, or as a coefficient, I should say. So this becomes this exponent comes out front as a coefficient. This is 0.09t times ln of e. This is why we did logs, right? I had to get this out of the exponent somehow, and taking logs of both sides allows me to do that. So I take logs of both sides, this comes out front, and now we can easily solve for t. Notice, by the way, ln of e is just 1. It's always equal to 1, so that's just 1, so I'm not going to write that anymore. And if I'm solving for t, divide both sides by 0.09, t would equal ln of 1.2 over 0.09. Again, notice I've rounded absolutely nothing yet. I'm going to do my rounding at the very end. But at this point now I plug things into a calculator, and I plug into a calculator. I'm going to round to 2 decimal places, and I get 2.06. What are my units? T is always in years, so 2.06 years. And I wanted to do one of these problems in particular to remind you that this is the hard case. Solving for T, or solving for R is sort of similarly hard. Solving for either of these things that are in the exponent requires you to take logs of both sides to get them out of the exponent. So if I pose another problem asking what's the rate, well, you'd have to do sort of similar stuff with logs. I could have posed this problem instead of compounding continuously. I could have given a number of compounding periods, and you would just use the other formula. A is P times 1 plus R over M to the MT. But mathematically, it would work out sort of similarly. You'd still have to take logs of both sides. We have one more concept left to discuss in this chapter, or in this section, which is annual percentage yield. So we've seen that compound interest is a very effective investment strategy. It leads to a larger account, a larger amount over the course of a year, assuming you compound several times during the year. It leads to a larger account balance, a larger value for A than just simple interest would after 1 year, right? So the annual percentage yield, sometimes called the true interest rate or the effective rate, is the simple interest rate that would lead to the same amount after 1 year as your compounding account has in it after 1 year. So what are we doing here? So what's the simple interest formula for A? It's P times 1 plus RT, right? And the formula for A for the compounding case is P times 1 plus R over M to the MT. This is the discrete case, not the continuous case. But I'm setting them equal to each other, and my question is, after 1 year, what value for R makes them equal? So let's see, we're going to set T equal to 1 year. So now I have just P times 1 plus R equals P times 1 plus R over M to the M, because T is 1. I can cancel P's from both sides, divide both sides by P, and if I'm solving for R, the rate that makes these two account balances the same, solving for R would then be 1 plus R over M to the M minus 1. And this guy, R, this is what we call APY, the annual percentage yield. It's the annual rate, the simple interest rate, that would lead to the same account balances, the same amount after 1 year as your continuous situation led to. Or sorry, not your continuous, but your compounding situation led to. So let's write this down, let's make a note of this, but you can also go through this process. You could go with the continuous case here, P times e to the RT. You could solve for that, and I'll just give you the end result right now. So APY. So if you solve for APY in either case, here's a summary of the results you'd have. The top one is the one we just found in the situation where we have M compounds per year. The annual percentage yield is equal to 1 plus R over M to the M minus 1. And if you solve the continuous case, you would just get this nice formula, APY is e to the R minus 1. So if you didn't understand what I was doing before or talking about, that's okay. These are just two very simple formulas you'll have to apply every now and then. And I'll show you how this works with a straightforward example. What is the APY for money invested at an annual rate of 5.15% compounded Well, we're in a compounded daily case, not the kind of compounded continuously case, so we're just gonna use this formula up here. And all we have to do is plug in a few values. APY is going to be 1 plus R, the rate. 5.15% as a decimal is 0.0515. Over the number of compounds per year, well, we're compounding daily, 360. To the power of m, the number of compounds per year, to the power of 360, minus 1. Plug this into a calculator, make sure you don't round anything until the very end, and you get that this is about 0.0528. Or as a percentage, multiplied by 100, 5.28%. So a little bit better than 5.15, as we would expect, because compounding interest with an extreme number of compounds like this daily is better than just a simple interest case. So if you were investing money for 1 year, and it was only going to, the interest was going to be compounded after 1 year, so paid out after 1 year, you would have to invest at a rate of 5.28% to match this situation where you've got 5.15% but compounding every single day and you're reinvesting every single day. We've still got 2 more sections to go, 5.3 and 5.4, but this is the end of compound interest.